Welcome back, students, to our second video lesson of the week. We are here with the same updates as usual. The vocabs will be fully updated because of my busy schedule. I'm actually going into my classroom again to finish up a few more things of cleaning the room out for me moving to another classroom next year. So I'm going to be doing that here in a little bit. So grades will not be fully updated until tomorrow with the recent vocab assignments. Do not forget, we have the Doppler worksheets that I mentioned the other day that are going to be due on Sunday at 11 p.m. And we've also got the notebook check number 3 with the unit quiz of the week being posted on Friday, which is tomorrow. Those will be due over the weekend with the notebook check being into next week as well. So just a few updates there. Otherwise, everybody get caught up and do your best to stay on track as we finish out the school year very soon here. Let's go to our Go Blue on page 16. Number 1, label the, and this is super important. Let me kind of move my screen out of the way. Super important. We've got to know the different parts of a wave, right? So we've got A, B, C, and D, labeling those separate parts from yesterday about, I think we plotted the parts of a wavelength, right, or a wave. And then 2, what type of star is the sun? That comes from the diagram we made yesterday with the star life cycle, parts that said sun, or what that is mentioning. And then 3, what are the 2 outcomes of a massive mass star, right? So the largest star you can get, we get 2 final outcomes. What could they possibly be? Take a moment, think about this, think about the answers, pause the video, and let's go ahead and check it out. Number 1, okay? A was the crest, that is the top of a wave. B is the amplitude, again, that's the range of a wave at rest. And then C is the wavelength, the wave from beginning to the very finish, beginning to beginning, right? And then for letter C, and then D is trough, that is the bottom of a wave. So again, those were the labeling the parts. Again, A is the crest, B is the amplitude, C is the wavelength, and D is the trough. Okay, 2, we're going to categorize our sun, our star, as a yellow, less massive main sequence star. We'll get into more of those details later on page, we have page 16, by the way, with our Go Blue answers, but it is a yellow, less massive main sequence star for number 2. And then 3, the 2 outcomes you can get with the massive stars, again, our star is not massive, it's more medium, less massive, are going to be black holes or neutron stars. If it's the most massive, we get a black hole. And then again, we can see here, this is for question number 1 again, right? Crest, trough, wavelength, amplitude. Okay, but we can see here again, with our most massive stars, we're going to get a black hole, or what we know as a high mass star, which is going to end up as a neutron star. So our answers again are going to be black holes or neutron stars, depending on how massive it is exactly. Okay, again, we needed these on page 13 from yesterday. Today's Go Blue is going to be on page 16. Okay, table of contents, go ahead and update that. We're finishing out Unit 8 here very soon, which is going to be pages 16 through 17, which we're going to categorize our star types. We did go over 2 yesterday, okay? But let's go ahead and do our first question of the day. What type of waves are often used in heat lamps? Is it A, ultraviolet? This is from our kind of our vocab listed from the wave types. Is it A, ultraviolet, B, microwaves, C, visible light, or D, infrared? Which best fits the idea of heat lamps? And the correct answer is going to be D, infrared. Again, infrared is going to be what creates and causes those lava lamps, right? Heat lamps. All right, so we have no video questions today, just 2 normal videos. We'll show through this. I do want to go over all the star types, and that's going to with 2 other practice questions, and that'll conclude our day. So we went over already yesterday, protostar. Again, you guys need to be writing this on page 15. If you need more room, use page 17 and just title this star types. Our first star we went over was protostar. That is the earliest, the infant stages of a star. Massive gas represents an early stage. Went over that already. And then stellar nebula, went over that already as well. So a cloud, a nebula is just a bunch of gases and elements that are super hot, stirring about in space. Usually, think of it as like the debris left over after the explosion of a star. That is a stellar, that is a nebula. This is stardust, right? Stardust that has been left in space from a star explosion. All right, our first new star of the day is what we call a red dwarf star, and it is just a small and relatively cool star on the main sequence. We'll go over this very soon, but color does determine how hot or cold the star is. Believe it or not, red is the coolest, and blue and or white is the hottest if my memory remains correct. But again, blue I think is the hottest. Think of the blue part of a flame, that is the hottest part of the flame, right? Our first star is a red dwarf star, okay? Let's go ahead and check out our birth of a star snippet here. We've seen this before, but again, I think it's important to see it twice because it does go over some of those new things we're discussing today. Again, it's going to show a few quick seconds of this as we continue with our different star types.
Look around the new star.
And again, remember, what star is that exactly that we see there, guys? What is the earliest star stage? The protostar, right?
Leaving the star naked and alone. If the disk survives, it could make planets. First by electrical forces as particles randomly collide and stick. Then by gravity as clumps attract each other.
So it's on you guys to make sure you watch all of that on your own. I cannot show too much of that because then YouTube will get mad and they might mess with my video. I don't want that happening because I want you guys to see all the videos, get all the content. Don't have to redo that, right? All right, let's move on back to our star types, guys. We're going to keep this concise and quick today. Okay. Next star is going to be what we call a white dwarf star. Okay, so dwarf meaning it is a smaller in size, right? And obviously the coloration has to do with its temperature, right? So this star expels most of its outer material, creating a planetary nebula as it burns up. Hot core of the star remains. So this is possibly one of the end results that our star could face, given the type of star it is and the size of star it is. So basically, you get the outer layers, the yellow or the red or whatever color the star may be, and then the outer layers fizzle away, and all you've got left is the core of that, which just kind of burns out, fizzles out like a battery, right? So that's a white dwarf star. Okay, we've all heard of black holes. Yes, black holes are the end products of stars. Stars can become black holes if they are large enough. And simply put, you guys saw this in your vocab already, a black hole is a region of space having a gravitational field so intense that no matter or radiation can escape. Light does not escape. Time, again, everything is fractured and altered, and it's a phenomena that is scary in a sense, but also so fascinating to many astronomers today. So very incredible stuff. We're going to get more into black hole science coming up here very soon as well. But that is the definition of a black hole. The main sequence star, this is the star that our sun is. So you might want to add that to this, okay? The type of star that our sun is. So using hydrogen in its core primarily, right? We can see our sun or some type of star that's like our sun at the bottom there. Stable balance of outward pressure from core. Again, what powers a star? Nuclear fusion, right? And then gravitational forces pushing inward. So again, this is the happy medium. This is the star that our sun is. And super important to know. We call this a main sequence star. Main sequence star. Okay, let's go to do practice problem number 2. Which of the following will probably be the final stage of our stars, the sun's life cycle? Kind of went over this a little bit earlier, I feel like. A, white dwarf, B, black hole, C, neutron star, or D, planetary nebula. Maybe easy to cancel one of those out because we haven't spoken on it yet. The correct answer is going to be an A, white dwarf. Again, most likely that our star will fizzle out, not explode in this massive supernova per se, but maybe just fizzle out like a battery ring on low, and then the white dwarf over time fizzles away as well. Okay, let's finish up with a couple more star types. One more question, we'll call it a day. Planetary nebula, how does this separate from a stellar nebula? Okay, well, this type of nebula is more ring-shaped, okay, from the expanding shell of gases around an aging star. So the stellar nebula, it's kind of all spread out and clumped and kind of like cotton candy flowing. But the planetary nebula, it's more organized and circular in its organization, right? So expanding shell of gas, it's like the shell forming around an aging star. So it's just kind of maybe what I think more likely our star could go through as opposed to a stellar nebula. All right, before we get into neutron star video, I'm going to show that video later. But let's talk about supernovas. We all know this, hopefully, from our vocab. Supernovas are the explosions of stars, right? So if a massive star, not likely our star, we're more or less massive, as life is over, we see this massive pink, purple coloration of gases superheated, exploding, becoming super bright deep into space. We've seen this with our Hubble Space Telescope. And it fades away from the view, leaving dust and gases behind. So again, supernova, another incredibly beautiful, fascinating feature we've seen in deep space. Okay, next we have our giant stars, particularly our red and blue giants, okay? These usually occur when the star is near the end of its life. We'll learn about this later, but the larger the star, the shorter its lifespan is, as opposed to the smaller the star. It burns a lot of helium, so we get more iron left over, as we've talked about before. And this star expands greatly in size because of the helium being heavier, right? So it just kind of condenses and expands and just kind of balloons as it gets to the end of its life, right? So red and blue giants. Let me make sure you guys know to highlight that yellow, or you need to write that part down. Oh, it always does that. It delays and then it moves the letters around. Okay, let's see that. 1 second, guys. Okay, and current. All right, let's finish this up. We've got our last star, I believe, maybe not, the neutron star. Quite fascinating and interesting here. It's created, it's like barely not a black hole, essentially, and it stays organized enough that it doesn't break and become a black hole. So massive, but not as massive, right? And still much more massive than our sun, our star. So created when giant stars die in supernovas and their cores collapse, so the core stays intact and produces protons and electrons that melt into each other to form neutrons. So protons positive, electrons negative. It's just this large kind of collection of those particles that make this neutral region of the core intact. So neutron star, quite beautiful and quite fascinating as well. And let's go before our last question of the day. Let's go and check out a quick snippet of the video, which is really cool. This was actually brand new to my class. This is only created 6 months ago, about neutron stars and what makes them so interesting and so unique in the first place.
Neutron stars are one of the most extreme and violent things in the universe. Giant atomic nuclei only a few kilometers in diameter, but as massive as stars. And they owe their existence to the death of something majestic.
All right, guys, so go ahead, please watch all of that. I watched, you know, I sat through just this morning all 8 minutes and 40 seconds, and it was nonstop, great visuals and very entertaining and informative. So please watch all of that. It'll really give you an in-depth understanding of the neutron star and all its details and why it's so unique and cool as well. So let's go ahead and finish up. That is it. I'm keeping things quick and to the point, guys. Basically, it was just, we just kind of ran through a bunch of new terms, all the different star types we're going to be learning about. All right. So our last question, which of the following colors has the lowest energy on the visible light spectrum? Also, I think meaning that it has the lowest frequency, if I'm not mistaken. A, violet, B, yellow, C, orange, or D, indigo. The correct answer, take a moment, is going to be C, orange. Again, the lower the frequency, the lower the energy, the higher the frequency, the higher the energy. Always remember Roy G. Biv. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, okay? And then don't forget, the lower the energy, the longer the wavelength, right? Or the lower the frequency, the longer the wavelength. So in this case, there's no red, but we have R, then Roy, okay? So it's O, so orange, O is next. Orange is the lowest of these options for energy. All right, guys, that concludes our lesson for today. Please be sure to complete the Doppler worksheet. That'll be due Sunday, and be ready for your next, the unit quiz and notebook check on Friday, which is tomorrow. I'll be posting those. If you guys have any questions, feel free to message me and let me know. Mr. Campbell, signing out.